Hello, everyone, and welcome to today's webinar, 3D Co-Cultures, Choosing the Best Systems and Analysis for Immuno-Oncology. I am Sydney Panilla of LabRoots, and I will be your moderator for today's webinar. Today's web seminar is presented by LabRoots and brought to you by Thermo Fisher Scientific. To learn more, visit thermofisher.com. As a reminder, we encourage you to participate today by submitting any questions you may have during the presentation. To do so, you can simply type them into the Ask a Question box and click Submit. We will answer as many questions as we have time for at the end of the presentation. You may also use the Ask a Question box to let us know if you are having any trouble seeing or hearing the presentation. Okay, I would now like to welcome our speaker for today's webinar, Darryl Turner, PhD in Veterinary Parasitology and Immunology, Principal Scientist at Concept Life Sciences. Darryl, you may now begin your presentation.
So this webinar today entitled 3D Co-Cultures, Choosing the Best System and Analysis for Immuno-Oncology. My name is Darryl Turner. The reason I wanted to do this topic was to discuss the methods that we are employing here at Concept Life Sciences to investigate these 3D co-cultures, the systems we're using, the challenges we've faced, and how we've overcome that by using these different systems. I'm a principal scientist with Concept Life Sciences. I have been with the business for over 10 years. Concept Life Sciences was originally made up of a few companies, and I was part of Aquila Biomedical, which made up part of Concept Life Sciences. Prior to that, I was in Aquila Biomedical's academic group, where we did a lot of work on EAE and T-cell biology. And prior to that, I was based in the Moredun Research Institute for 4 years, where I also did my PhD, which is a lot more veterinary focused. These days, my main areas of focus are around immune cell biology and cell biology in general, and developing complex assay models to look at different modes of action, look at different compound actions within these systems, specifically focused around immuno-oncology and autoimmunity, but I do branch out into other areas as well. Our Concept Life Sciences, we are a UK-based CRO. We offer a wide range of services around drug discovery, including target validation, hit identification, and candidate selection. Our sites cover chemistry, ADME, and biology is where I sit. And we pride ourselves on expert-to-expert communication and developing our clients' campaigns around data generation and material generation. On to today's topic, essentially what I'm going to discuss is an introduction to 3D culture. Why do we use it? What's the advantages and disadvantages? Then going on to some of the methods that we have employed at Concept Life Sciences around spheroid generation, either single spheroid or multispheroid, the ways we go about analysing them, what co-cultures look like, and then the pros and cons of the two methods, using a few examples of the data that we have generated. Why would we want to do 3D co-culture? So essentially 3D culture is a little bit more advanced than 2D. So in 2D, all the cells are essentially in a monolayer. They have equal exposure to anything in the supernatants, and cell-to-cell contact is very, very limited. So there's very little communication other than at those contact points, assuming they're right next to each other. And they have a forced organization and polarity. In 3D culture, essentially those interactions become a lot more complex. So essentially cells at the center and on the edge have obviously different exposures to what's in the supernatants. The interactions between the cells are a lot more complex. There's not just a single border interaction. They've got contacts pretty much all the way around, unless they're right on the edge of the sphere. And essentially this hopefully mimics much more of the tumor microenvironment that we obviously want to investigate. And obviously any nutrients, and also anything that's excreted by the cells, there's a gradient of that. So the edges and the center are very different to each other. When we're talking about co-culture, essentially we're talking not just one cell type, we're looking to incorporate many cell types. So you can essentially incorporate as many cell types as you want, but we're going to talk relatively simply today around about 2 main types, as well as incorporating immune cells at a later stage. The principal readouts we have been using here at Concept Life Sciences are around about imaging, so time-lapse imaging, as well as high-content imaging. And then also we've employed flow cytometry when we've taken the cultures apart to look at specifically the immune cell components that we've been employing. And then other endpoint assays, which are ELISAs, multiplex, and cell viability assays, but we'll probably discuss these a lot less. That's simple. So let's start with a single cell type and forming single spheroids. So essentially what you do, create a single cell suspension, apply it to a UVOM, ultra low attachment plate, and essentially pre-centrifugation to bring the cells together at the bottom. And essentially there are other ways of doing this, but you can, like using hanging job or low gravity methods, but this is the method we've employed. Essentially we want to look at some of the earlier aspects as well, and essentially those methods don't allow that early observation. You can incorporate things like ECM additives like Geltrex, Matrigel, collagen into your media to kind of help form spheroids, but obviously you're adding a single component, and is that the right one? Who knows? And then the other challenge you have is what the cells want to do themselves. So some cells want to form spheroids in this way, others don't. BT474, for example, does form a very normal, very tight spheroid, and it does look like a sphere. Again, A549s also look like spheres, and this example here is one of the pictures we've got. This has been labelled up with Drac7, which is a viability dye, so you can see the necrotic core, and these are quite large. This will be over 500,000 in size. And essentially it does look like a sphere, but you can really disrupt that if you really want to with some vigorous pipetting. The other group are essentially loose aggregates. MCF7 falls into this group, and essentially they just don't want to form these large spheroids. They essentially form these small clusters at the bottom of the plate. The small clusters grow, but they break apart, and they just don't want to form a sphere. And then the final group are the ones that just never want to form any sort of cell-to-cell connection on their own. So A375s and PC3s fall into this category, and essentially they grow as a single cell suspension at the bottom of the plate. They do grow, but they're just not forming those cell-to-cell attachments. One of the other challenges with these single spheroid systems is if you're looking at time-lapse imaging, is when you do a feed, you can dislodge them. They can move slightly out of the field of focus, so that can prove a slight challenge. But you only tend to lose a couple of time points, and they do gradually move back in to the field of view. Taking the complexity to one level extra by incorporating another cell type. So what we chose to incorporate first was fibroblasts, and the reason we did this is essentially fibroblasts form a large component of the cancer microenvironment. A lot of cancers share this. You can get quite large fibrous areas and lots of fibroblasts in casts, and they do talk to each other. So fibroblasts and cancer cells do talk to each other and can affect each other. And one of the observations we made when we started incorporating these was that cells that didn't form spheres started rapidly forming spheres. So A375, MCF7 started forming spheres. MCF7 here is an example. The fibroblasts have been labelled up with PKH67, which is a green fluorescent dye, and essentially they form the central core, and then you've got a region of cancer cells around that core of fibroblasts. PC3s, which didn't form any sort of aggregate at all, as soon as we incorporated fibroblasts, we start getting really tight aggregates, and they seem to be the opposite way around compared to MCF7 and a lot of the other epithelial cells, where you get a core of the cancer cells, and then the fibroblasts form the outside of the aggregate. The other thing we've noticed is that these fibroblasts seem to affect how the cancer cells grow. So BT474 is a good example of this. Again, here we have cells, the fibroblasts labelled up in green, PKH67, and as you'll see, associated with each of those green dots is this outgrowth of cancer cells here. So there's 4 of them here, and obviously that suggests that there is some communication. The fibroblasts are actually directly affecting how those cells are growing. And then you can also get much more complex structures forming, so HepG2s. Looking at here, in this case, we've got a band of cancer cells are labelled in red, so that's pan-CK, and we've got the fibroblasts labelled with PGFR beta alpha. And essentially, you can see these bands of cells, and they're obviously quite complex interactions ongoing here. And by incorporating cells rather than just incorporating ECM, we obviously can control the number of those cells that go in, so we can go down to physiological levels. In the case of the HepG2s here, we've got essentially one fibroblast for every 19 cancer cells, which is kind of roughly where the liver sits. So if you look at liver, then you have about one stellate to every 19 parenchyma cells. Or you can go absolutely the other way. You can incorporate lots of fibroblasts and have very few cancer cells, essentially mimic that really fibrotic environment. One thing we have noticed is the fibroblasts tend to be relatively stable through this, and they don't tend to change too much structurally. So once they're there, they don't really change very much. They don't move around too much. They form their band, and they don't really grow that strongly. So without any intervention anyway. So something you will notice if you do incorporate fibroblasts is the speed that these spheroids form. So here's just an example of A549. So we have 5,000 cells in both these cases, so 5,000 A549s or 5,000 cells in total with 4,000 A549s and 1,000 fibroblasts, which are MRC5s in this case. And as you can see, after 12 hours, you can essentially still see the single cells. It has started to contract a little bit, but it's not too far. It's not gone too far. But with the incorporation of the fibroblasts, it's contracted quite a lot already. And after 6 days, essentially there's not that big a difference between the spheroid size. They are very, very similar in size. I've had to increase the contrast here because these do disappear a little bit on the images, but I've managed to increase the contrast enough so you can just see the border of it. So the other route we have taken is to use synthetic hydrogels, such as Petimatrix. The advantage of this is that we can incorporate a lot more cells in a well, so you can have higher densities of cells. You get lots of small spheroids, but you can have a lot more cells, so if you're looking for excreting components, it becomes a lot easier. The reason we've gone down the use of synthetic hydrogels is essentially they're a lot more tunable, so you can get different stiffnesses, you can get different ECM motifs incorporated. So the one we've used quite heavily is RGD based, but you can get Igorov and others like laminin type fibrin, all these sorts of tunable components. And obviously, because they're synthetic, they're a lot more consistent. So things like Matrigel, Geltrix, they have a animal component, so they're not always consistent over time. So there are small changes in them. And when it comes to feeding, once the gels are set, it's actually relatively easy to feed. You're not going to just move these cells around randomly. They're embedded in the gel. So essentially, it's easier to kind of image them over time in a single position. One of the considerations, though, when using this is when they're getting incorporated into that gel, is because it has to gel, it does go through a change. So Petimatrix goes through an alkaline change, but you can overcome this by doing a quick couple of feeds over the first few hours just to kind of get rid of any of that alkalinity, and that keeps the cells happy for a much greater period of time. So when setting these up, it tends to take a bit longer, but they are stable for a very long period of time. We have cultured out to over 21 days using these systems. But as you can see, these are just a couple of examples of some of the images we have taken. On the left here, we have HepG2s, which have been co-cultured with stellates and THP1 cells, and we've got quite a few small spheroids. The HepG2s in this case have been fat-loaded, and we can see that they've been stained with Nile red, so they're essentially fluorescing green, so they're polar lipids. And then on the right here, we have a much more detailed focus. We've taken a histological examination of some of these spheres, and you can see how the spheres look. And this is a dab stain for collagen, and you can see the collagen all the way through the actual centre of the sphere. There does seem to be some background with the Petri matrix on the outside, but within the sphere you can see these collagen fibrils. I've noticed when using these hydrogels is the way that the cells behave and grow. So A549s, as you can see here, the cells form small spheres. The spheres just sit where they start, and they just gradually grow over time. So you can see that they just gradually get a little bit larger. PC3s, on the other hand, seem to behave differently, and large portions of them seem to want to migrate throughout the matrigel. So you can see these big clusters starting to form, and you can see them migrating over a period of time. And it is quite rapidly moving around. I'm not sure why, but it's again just something we have observed. It might influence what cell types you choose for your experiments. I am aware that there are other advanced methods for doing these 3D co-cultures. So you can employ things like cell printing. So that is essentially the hydrogels taken to the next level of precisely placing cells next to each other using a printing system. And the other thing you can do is incorporate microfluidics. Obviously, that's difficult because it obviously requires specialized plastic and equipment, but it does mean that you can look at how fluid dynamics and slight passing to like mimicking circulation can have an effect on the growth of these sorts of structures. So, but I do know they exist, so just we haven't quite yet employed them at Concept Life Sciences. Have your spheres, you then want to be able to manipulate them. So essentially what you do is you generate your sphere, allow it to form over a few days, and then expose it to something. So in this case, in simple spheroid system, simplest thing to do is just expose it to a compound, and then assess things like viability, growth, and all these sorts of things. So looking at some data associated with this, so looking at the very basic single cell type spheroid structures, as I said earlier, different cells respond differently. So A375, A549, and BT474, all in 2D, show a dose response curve in viability to something like doxorubicin. A375, as I said earlier, kinds of forms of suspension, they do keep growing, and we see a small shift in EC50, but it's just a shift to the right, so it requires a bit more of the compound, but it is a gradual change. A549, which form those more tight aggregates, again you get a dose response curve, but essentially it's a bit more, okay, we'll have a little bit of response, and then once we get to a really cytotoxic level, then it essentially just falls off a cliff, and essentially a cytotoxic level completely. And then BT474s, we never actually found the cytotoxic limit. They were quite happy to sit in the equivalent concentration all the way through, so they just did not respond to it in that same way. Incorporated fibroblasts doesn't seem to change this too much. So unless you start getting up to the more extreme, so like absolute numbers of like where the ratio is more fibroblasts rather than cancer cell. So again, essentially it's probably the same method, but looking at it, and as you can see, it's like at lower ratios, so just the cancer cells alone, or just a few up to 50-50 mixture. Essentially, the curves are very, very similar to each other. And then as soon as you start moving away, you start getting once you're beyond that 50% ratio, it looks like actually the cancer cells are less dominant, and essentially the curve starts switching more to what the response of the fibroblasts are, which is the black line. And it's the same case with both of these. So A375 and A549 both do something very similar. It's just slightly different dynamics of it. So that was looking at the effect of compounds directly on the sphere's growth and the way that they respond. The next level is to kind of incorporate other cell types. So once you form your sphere, you can add other cells to that, so PBMCs or T cells. And the question we had here was, can you manipulate the way that they respond and how they interact with that sphere? Can they change the growth of that sphere directly themselves? So the incorporation of immune cells is to look at their direct effect on the cancer cell growth. By incorporating them, can we manipulate how those immune cells respond? Can we change their effectiveness? Just by incorporating PBMCs or T cells, they won't just do it on their own. They will just sit there and ignore each other. This is just in 2D setting, but by adding something simple as anti-CD3, you can obviously activate the T cells, and they will go around and start killing the cancer cell lines, A549s here, and that aligns with the increase in apoptotic A549s. So can we manipulate that further by incorporating other activators and methods? So things like TNF alpha, interferon alpha can have direct effects on their own on cancer cell growth. So again, here's A549s. This red line here is an example of TNF alpha, and you can see it has slowed the growth of those A549s. Incorporation of other cytokines to activate different components of the PBMCs. So if you don't add any like TCR activation, but you add a mixture of IL-12 and IL-18, they will synergize to each other and activate the NK components, so they all start killing. And then on top of that, you can also start incorporating again the anti-CD3 to have that T cell component, and again things start synergizing. IL-2, IL-12, IL-15 will all further increase that T cell activation, and again TNF alpha, interferon alpha, and all these things start synergizing as well. So you get a multiple levels of activation. But that's in a 2D setting. Obviously, exposures are essentially uniform. So one cell will get exposed to T cell, another get exposed to NK. There's not very much migration happening. You can start doing the same experiment in a 3D setting. Allow the spheres to form, and then incorporate the PBMCs. If you just incorporate PBMCs, they do very little. They'll just sit there on the outside of the sphere and not do an awful lot. But as soon as you start activating and changing the activation status of those PBMCs, you will start seeing changes in the sphere. So anti-CD3 again alone is sufficient to kind of reduce the growth of that sphere and start breaking down. Anti-CD3 plus the cytokine can have a much more devastating effect on the sphere, and you can see how it's almost completely broken down. You've just got individual cells throughout, which the immune cells will start dealing with. And obviously this can be imaged over time. You can see it happening over time. Experiments similar to what we did with 2D by just manipulating which cells got activated, and by incorporating cytokines. Again, TNF alpha, interferon alpha had their own direct effect. Again, it was quite a bit more dramatic than it was in the 2D setting. Incorporation of R12 and IL-18 without any TCR stimulus again was quite effective. R12 on its own was quite effective in this setting, and then TCR on top of that made it even more effective as well. So again, we were mimicking what we were there, but essentially the effects were essentially enlarged. We can now manipulate the activation status of these immune cells, but obviously that's just by incorporating cytokines. Can we have more relevant treatment effects? So one of the things we were struggling with in 2D was the incorporation of things like anti-PD-1, where we're only getting very, very small shifts in the activity of the T cells. So we thought, well, can we change that? Does it look different in a 3D setting? And it can be done. What we had to do though was activate the PDL1 on the A549s by incorporating interferon gamma. Once we incorporated interferon gamma into the culture system, so during the development of the spheres, that was sufficient to then allow us to manipulate. So when we incorporated anti-PD-1 into the system, then we got a significant reduction in the growth and the viability of those spheres. When we didn't have the interferon gamma, then there was no effect, so it's similar to what we saw in the 2D system. Would that interferon gamma have an effect? Well, essentially, A549s themselves don't readily express high levels of PDL1 on the surface normally, but if they get exposed to an inflammatory signal like interferon gamma, then they will upregulate that. So here, just a couple of flow plots to demonstrate that. So A549s unstimulated, you get very low levels of PD-L1. As soon as you expose them to interferon gamma overnight, the vast majority of them are expressing quite high levels of PD-L1. So we thought, well, okay, what happens if we go look at another cell type? So PC3s are documented to express PD-L1. Again, we've shown this increasing exposing to interferon gamma doesn't make that big a difference. You just essentially it's slightly higher on a few of the cells. Read that into the 3D spheroid system, it didn't work the same, and we're not sure why. It could be a few intrinsic differences in the way that spheres form. So, as I said, the A549s are on the outside, the fibroblasts are in the middle. The PC3s, we think it's the other way around. The fibroblasts are on the outside and PC3s are in the middle. And we think it could be that stuff isn't getting in, so those antibodies just physically can't penetrate in to manipulate this. The PBMCs can get in, they can do their job, they are starting to kill, but the mechanism isn't quite there. So that's just a few of our thoughts to investigate that further. The challenge we faced is that when we were setting these up, we thought, well, okay, maybe activated PBMCs might be better. Certainly in the 2D system, if you put activated PBMCs onto the system, they will quite readily wipe out the target cells quite rapidly. It makes it very difficult to manipulate because it's such a rapid response. In the 3D system, that doesn't appear to happen quite so readily. If anything, the PBMCs are completely ineffective. And we're not sure why, but it could be a number of reasons. I know we have now changed these PBMCs, so by activating them, they're not the same as what the fresh ones are like. There's potential loss of function, or we might be exhausting them. There might be a few other things that are going on. But the other thing, when you look at these 3D systems, is the vast majority of the cells just sit outside the sphere. They don't. It's only very few numbers of them actually get in the sphere that actually have the direct interaction. A question of, okay, what is actually entering these spheres? Is it different? So we did that through flow cytometry. So we had to break down the spheres. We collected the spheres. We left the cells that weren't inside the sphere. We examined them separately, but took the spheres and degraded them with trypsin to kind of break the sphere apart and try and release into a single cell suspension again. When we were doing that with this single sphere system, what we were finding is to get anything meaningful, we would need to incorporate lots of spheres just to get enough data to be able to have a look to see what the immune cells were doing, because there were so few of them in the sphere itself. And one of the things we did notice was, well, actually, if we did pre-activate the PBMCs, they were actually able to get into the sphere. So obviously, they're happy, they're healthy. We did a viability diet, and they were healthy. But relatively low numbers of them can enter, and the addition of anti-CD3 made actually no extra addition. But when we added fresh PBMCs and we activated those with anti-CD3, there was a greater proportion that were going in. Obviously, this has got no error bars because essentially we had to incorporate so many of the spheres together. We actually lost our N number, but the vast majority of those that do enter are T cells. So the greatest majority of those are T cells. The one thing we did find that we'd lost was we'd actually lost the myeloid component. So when we use fresh PBMCs, there are CD11Bs getting into the system, but when we pre-activated, those CD11Bs have been lost. And that kind of makes sense because during that pre-activation process, essentially those CD11Bs have been allowed to adhere down to the plastic, and essentially all we're really transferring are the true suspension cells like the B cells, the T cells, and the NKs. And so we seem to have lost that, and that seems to be the biggest difference here. So that seems to be something that manipulates how these cells are then going to respond. So we have done these similar experiments in hydrogels. The advantage here is essentially once you overlay the PBMCs, all of them have the potential to interact with those spheres. They can all migrate in and find a sphere and interact with it. Difficulty here is if you want to do time-lapse imaging, it's a little bit more difficult, especially if you want to do lots. It becomes a challenge. But at the end, you can still have a look at the cells. So there's a couple of examples here of different treatments. So spheres just exposed to PBMCs, the spheres themselves survive. So the A549s here have been labelled with RFP, and they're nice red. They're quite happy, small spheres throughout. When the PBMCs have been activated, actually these spheres are now dying. So there is a loss of viability with those. So there's a caspase 3-7 die again, and the A549s are now dying. When it came to flow cytometry, it was actually a lot easier to get enough events to kind of make numbers a lot more useful. So rather than incorporating 6 wells to generate a single data point, we only need a single well to kind of get the same level of immune cell data. And when we look at the signal spheres themselves, so just spheres alone, there's not very many dead cells at all. So there's none really apoptotic. Incorporation of PBMCs, we do lose a few cells are dying. But then when we add the anti-CD3, similar to what we get in the picture above, a lot of the cells are starting to show signs of death and apoptosis. And when we look at the immune cell component, it's a lot easier to kind of get the populations and isolate them and get meaningful numbers of them. So here's just CD4, CD8, and this just came from a single well. So whereas previously it was taking 6 wells with single spheroids to get decent numbers of cells to actually analyze, in these hydrogel systems, it's a lot easier to get to high numbers. And essentially what you can do, since you use this system for, you can essentially go, okay, can we manipulate, and do I want to have a look at the immune cell component, or do I just want to look at the sphere? And that decides how you want to move forward with these systems. So the other thing you can do is look at imaging these spheres at the end, so you can see where things are directly within the sphere. And obviously that requires some confocal imaging, because they are complex structures, and light needs to be able to penetrate, and you need to be able to work out where things are. However, we have found some challenges here. So if you use direct labeling, so if you directly label the cells with PKH dyes, TFSC, then we can work out where things are. So the example on the left here, we've labelled up the fibroblasts with PKH dye, and the PBMCs are in green, and you can see a few of those throughout the sphere. So you can, obviously the light can get through. When we've tried to kind of label up things at the end of the experiment, just using antibody stains, what we found is that it's actually become challenging. And we think the antibodies just can't penetrate more than a couple of cells through, and essentially see a shell. And you can see that on the right here. So this is the image I saw earlier, and said earlier that I would explain why it was just the surface. And essentially this is why, because essentially you can see there's a hollow. So this is a 3D rendered image of the stack that we took, and you can see how it's hollow on the inside. So we've got a nice surface staining, but actually we've got no depth into it, so we can't see much further than that. So that's one of the challenges here. And obviously when you're using the hydrogel systems, that's less of an issue because the spheres aren't so big. So essentially the materials can penetrate in more easily. Do is take your spheres and embed them. So, and again, do histological staining. So this gets you around the need to kind of just stain the outside of the sphere. You can essentially embed them and have a look throughout. But obviously, you're only looking at a single plane, but it is useful because you can stain them up this way, and it does work. And essentially, here's an example of ones we have done. This is just a sphere on its own with no PBMCs. And on the right, this is one that got exposed to PBMCs, and you can see T cells and macrophages throughout. So the T cells are labelled in white, the macrophages labelled in CD68 in red, and CD45 is a total immune cell marker, and you can see how they're throughout the entire section there. So similar to what we saw with flow cytometry, you need a lot of individual spheres to make anything meaningful, so it helps the person doing the sectioning if there's lots of them together, because essentially they're easier to find, so they can section through them. The other option is, again, use the hydrogel option, and you can essentially embed the entirety of the hydrogel and section through that. And this is a bit easier, and it's easier for technicians to find and do the cuts. This is just an example here of ones we have done. Again, the cancer cells are labeled up PANCK and are purple, and you can see them embedded throughout the image. And on the right here is ones that are exposed to activated PBMCs, and you can see the T cells labeled with anti-CD3, and they're white, and you can see how they're clustered around these what were cancer cells, clusters and spheroids, and they're obviously interacting directly. And obviously you can do other histological stains as well, so that H&Es, so again you can see how the spheroids look, and then how they look when they've been exposed to PBMCs, and you can see how they're heavily disrupted, and the PBMCs are throughout the spheroid space. The majority of this presentation is focused on immuno-oncology setting. You can look at other settings as well. So we've started into liver fibrosis and trying to use similar methodologies to kind of incorporate this, because 3D setting here is very, very important. 2D liver fibrosis is very difficult to manipulate, whereas in 3D we do appear to be getting some ability to manipulate this and see treatment effects. And we found this a lot easier in hydrogels when we're looking at single spheres. Again, it was a signal noise ratio. Essentially, with a single sphere, getting enough signal to be able to see changes was difficult. As soon as we went up to hydrogels incorporating more cells, then the readouts became a lot easier for us to do. Example of that, we've currently got this system using just cell lines at the moment, so HepG2s, stellates as the replacement for the fibroblasts, and we've also incorporated macrophages directly. In this case, it's THP1s that have been PMA treated. Again, we allow the cells to interact and form their 3D structures over a week before we start triggering anything else. So before we trigger any, in this case, MASH protocols. And the main readouts that we've been incorporating here are looking at neutral lipid incorporation, cytokine release, and procollagen. And again, here we can see how this has changed. So by incorporating fat into the media, essentially we're able to induce MASH, and then we're able to do compound treatment, so expose these spheres when they're treated with MASH with compounds to see if we can manipulate that MASH phenotype. And essentially things like elafibranor and gallinosirtib have had a direct effect on the neutral lipid loading, so they've prevented that neutral lipid loading. Things like selonsertib have had a direct effect on cytokine production, so that effect of the macrophage components. And then selonsertib also had direct effect on collagen production, so it reduced collagen, as well as elafibranor did this to a lesser extent over a longer period of time. A few examples of the methods we've employed. Essentially, the takeaway message here is when to employ the different methods, and it all comes down to why and what you're investigating. So if you're just looking directly at the spheroid and how that's changing and its growth, actually the single spheroid system works really, really nicely. So if you just want to see how its growth dynamics change, that works really well. But when you then want to look at the immune cell component, it becomes more challenging, because essentially breaking those apart with enzymatic action, it becomes difficult. That's when the multi-spheroid system also kind of lends itself to being better, because essentially you can then look at how those immune cells are actually interacting with these spheres much more easily, because you can get more of them back. It's easier to get them back to look at it. What we have shown is you can incorporate very many different types of cells. Obviously here we've just done fibroblasts, but you can start adding more cells, and I look to do that hopefully in the future. By including these cells, you can, rather than just adding ECM components, you've got a lot more ability to manipulate the numbers, the proportions that are going in, so you can have a lot more control of that, so that's a lot easier. And then the other thing we've noticed, as this comes down again to the single spheroid and multi-spheroid system, is substance penetration. So the single spheroids, large substances like antibodies, are finding it difficult to penetrate through. and we can see that when we try to do sort of imaging techniques, whereas the multivariate system, that's less of a problem, essentially, because essentially it's a much smaller system, but it does mean you can look at, again, different modes of action. And then there's obviously a lot of other things that you could potentially do, and look at how these cells migrate in. Again, the single cell system is difficult. You can see where they go, but again, with the multi-cell system, you can obviously label a lot more examples of cells that are moving around. So there are advantages and disadvantages there. So hopefully that has helped go through here. I'd like to thank you today for listening, and for Thermo Scientific Fisher for letting us do this webinar. I'd like to mention a few members of the team that have heavily contributed to this. So over the last couple of years, I've had a couple of students have helped with this. So Rosie Craven and Mary McBride, who have heavily been involved in generating the data. Histology guys, Chris Mills and Julia, have helped them generate some of these images, as well as the rest of the immunology team, just to name a few: Justina, Andrew, and Emma, who have helped supervise this work as well as everyone else at CLS, especially at Edinburgh and throughout the company itself. Any questions?
All right. Thank you very much, Darryl, for your informative presentation. We will now move into the Q&A portion of the webinar. So if you happen to have a question that you would like to ask, please go ahead and do so now. Just type your question into the Ask a Question box and click Submit. We will answer as many of your questions as we have time for. Okay, the first question that we have here says, what are the current technical challenges and limitations in integrating iPSC-derived cells into 3D models?
Yeah, so this is something we're just about to start embarking on ourselves. I think part of it is choosing what stage those cells need to be incorporated into these models. So I think that's going to be very tissue dependent. Obviously, the first one we're going after at the moment is liver. But like I say, we're just about to start going, so we're thinking we might need to go like the kind of just before they're going through their final differentiation, so start incorporating them at that point, and then start incorporating the other cells alongside it as well. That's going to be a lot more difficult, I think, and there's a few questions we need to answer there ourselves as well.
Perfect. Thank you. We have a quick comment here. Somebody said, thanks for the tips, great data. The next question that we have says, which computational and mathematical approaches are typically applied to analyze and model 3D single/multi-spheroids?
This is a bit beyond my expertise. We are starting to get into that ourselves and trying to model especially around the imaging. I say the things that I'm mostly interested in are the immune cell components. So I tend to want to find those. So I tend to degrade the system. But I say we are using sort of image analysis programs. So I know that Thermo have their Mira program, which works quite well alongside this to kind of get those sorts of answers. And our histology guys here have got quite a lot of experience with doing image analysis and looking at how things are structured to get with each other, and do lots of image analysis. I'm not sure about the mathematical models, but yeah, I think it all comes down to how you do that image analysis in the first place.
Okay, great. The next question that we have here says, when selecting between scaffold-based and scaffold-free 3D culture methods, what factors most strongly influence your choice for a given project?
So that's coming down to what the cells do themselves. So if they're happy with that scaffold, and we're only interested in what they're doing, then I'm quite happy to leave the scaffolds out. But let's say things like A375s, PC3s, and I know things like MDA, NB231s also just don't like forming these spheres on their own. So you kind of need some extra sort of structure there for them. Like I say, I know those three, you can add extra bits to the media and they will form it. But I say it comes down to what you want at the end of the day. What's the question you're trying to answer? If you're looking at spheroid growth, then obviously if they need the extra support, you're gonna have to put it there. If they don't, I wouldn't put it there unless you absolutely need it to be. I say it just comes down to what your question is and what cells types you're using. And the fibroblasts, when we incorporated them, obviously they are able to start making some of those structures themselves. So actually, it's giving that slightly more natural interaction. So we're going to be incorporating lots of other different. So we're looking at incorporating casts directly from patients and things as well into these systems to see how they get involved as well. So there's lots of things you can do, and then you can also, the more cells you get incorporated in, the better. I say T cells, when we've done the single spheres, if you add those, they just sit on the outside unless they get direct contact with the sphere, and they might move in. With this hydrogels and things, if you put them in, they've all got the opportunity to migrate through and migrate to where you want them to. So that's, as I say, it depends on what your question really is.
Okay, great. The next question that we have here says, how do you maintain functional immune cell activity over extended culture periods in 3D systems?
So when we've incorporated macrophages, that's not been an issue. So let's say the system we had there at the end, looking at the liver fibrosis, we've actually done primary macrophages in that as well. So we've generated the macrophages beforehand just by differentiating monocytes with MCSF, collecting them at the end, and then incorporating them directly into the hydrogel with the other cells. And essentially, the support they need seems to be sufficient there. We didn't actually add any further supplementation there, and we've found activity over 3 weeks later just by stimulating, and they're the only cells in there that can respond, because if they're not there, then we won't get the response we're looking for. T cells, again, until they become activated, are probably not going to need very much support. They will quite happily sit in culture for long periods. It's only when you start activating them. NKs might need a bit more support if you're looking at those. Let's say, again, it just comes down to what you think you need to put into your cultures. It depends on how well activated you want them to become. But I think, depending on what your question is, I would incorporate immune cells as and when. Like macrophages have from the start, because then they've got a chance to talk to other cells and get the communication from the other cells around them, so that will influence how they behave. Whereas things like T cells are much more likely to come in as part of a response. So actually adding them later and seeing how they then respond to other things in there, then that's a way forward there.
All right, great. The next one we have here says, do you need to activate monocytes for them to enter a tumor cell sphere?
We haven't had to. They entered on their own quite readily. And then when we've used the hydrogels, so we've incorporated macrophages directly into that system themselves. So I don't think they necessarily need that. If you want to add them, they will gradually change, and they'll be obviously manipulated directly with the cytokines around them. So I don't think it's as strictly necessary, but you can influence it yourself by adding extra things around them.
Okay. Next question says, for the 3D spheroid tumor killing assays, what platform do you use? Do you favor 3D TKA over 2D? And is there a setting in which you'd use 2D over 3D?
So 3D I think is more useful if you're kind of trying to ask questions about whether cells can penetrate into a system. Certainly seems to be something that we've got questions around. One of the things, like I say, one of the things we had questions of is the example of using certain modes of actions, like looking at anti-PD-1 treatments. When we did that in 2D, we got zero response. So like you could put the anti-PD-1 in, and we think part of that might be timing issues. If you're just looking at general activation, then 2D works absolutely fine. It works really well. And one of the things worth looking at is, so some people look at is what do CAR Ts do in this situation. Obviously, CAR Ts, one of the big questions about those is whether or not they can penetrate in and get to where they need to be. So a 3D setting there is a bit more important for those.
Okay, perfect. Next one says, do you encounter problems regarding the choice of cell culture medium when co-culturing different cell types? What would be your recommendation regarding choice of medium for co-culture of cancer with primary cells?
So again, this is something we're starting to deal with again with iPSCs and how we start incorporating lots of different cell types together. Obviously, different cells have their own different needs. The one that we've done, so that liver fibrosis one, the nice thing there is it's MEM based. So actually, the thing we're having to add more of is the things that the stellates want. So actually using their media over the Hep G2 media has worked really nicely. The Hep G2s are quite happy. And again, this will come down to what your cell types of choice are. There's no reason why you can't add those growth factors straight to your media. Obviously, one of the things we're trying to do is reduce the amount of things like serum and stuff we're adding to these systems, because obviously that's got factors that we've got little control over. But again, iPSCs, we're going to have to go completely serum free, so it's something we're trying to limit as well. But yeah, there's a few questions there. Let's say immune cells, we've not had any issues with, but yeah, other cell types, I think will probably need their own support mechanisms. One of the other cell types I want to get in potentially is like endothelial cells and see how they respond in these systems. And I know that we're going to potentially have to incorporate their growth factors in as well. But I say it's just a case of mixes of them seem to work quite well, or you can favor one over the other. So yeah, I say it comes down to experimentation there.
Okay, great. We are getting a lot of really great questions in here. So it looks like we have time for a couple more here. This next one says, have you ever tried to incorporate T cells in spheroids instead of adding them on top?
I've not done that yet. It's not been a question we've been asked to solve yet. There's no reason why you couldn't. Say they probably would go in. I think the reluctance I've had there is essentially coming from my background is that I know that T cells tend to enter a system rather than already be there. So there's no reason why you can't. And obviously then you could ask questions about whether or not things can get in to activate them, especially in those really dense spheres. But yeah, it's certainly doable. It'd be interesting to see how they distribute and things, because obviously the cancer cells are going to move up around them quite rapidly. Whether or not the T cells go with them, I don't know.
Okay, so we will go ahead and wrap up with this final question here. This one says, what's your experience of using THP1 derived macrophages to evaluate immune system action in vitro?
So that's worked quite nicely for us as a model system. I know activating them with PMA and things is not ideal, and THP1s prefer to be, when they're down that road, are probably more likely to be pro-inflammatory. And I say some of these things we've been culturing that for long periods of time. This is one of the reasons why I've already tried to ask the question of, can we put primary macrophages in there to kind of support that as a potential switch for us, because that's going to become important for us. But as a quick test to make sure that all your cells are working together, THP1 is obviously a cheap solution to that, and we've had no issues there. It's just that, yeah, I'm well aware that they're probably going to be more on the pro-inflammatory side.
Okay, wonderful. Well, thank you again, Darryl, for your time today and for your important research. We would also like to thank LabRoots and our sponsor, Thermo Fisher Scientific, for underwriting today's educational webinar. Before we go, I would like to thank the audience for joining us today and for their very interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webinar can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye, everybody.